So in today's lesson, we're going to talk about reduction potentials. What we're going to do is take our current knowledge of electrochemistry and we're going to quantify it. We're going to add some math to the situation because the math allows us to kind of take this to a different level and make some predictions. So you'll remember that in class, when we built our galvanic cell, we were able to measure the cell potential using a voltmeter, right? We saw that little needle kind of move, showing us that in fact there was a potential difference that was created in our cell. Now, alternatively, you may have seen one of these doohickeys somewhere. It's called a multimeter, and it has lots of different options on its dial for you to measure, for example, resistance and so on and so forth. So those are both great instruments to measure the cell potential across a galvanic cell. And so presumably scientists over time would want to have access to some standardized values for cell potentials, just to kind of have an idea, okay, if I stick these two reactants together, how are they going to react? And is that going to generate electricity in a spontaneous reaction, or is that going to be non-spontaneous and I'm going to need to add a little bit of current to make that happen? So I want you to grab your redox chart. I've got one here. And I want you to notice that there's a component of it that we haven't used yet, and that is down here, these values for cell potential. Now you'll notice that the symbol is that E with a little kind of degree symbol, and we've seen that before in our thermo unit when we were looking at standard enthalpies of formation. So that little sort of like degree symbol indicates that that value is standardized. And what does standardized mean? It means that it's done under a set of identified conditions. So let's look and see what the identified conditions are in this case. It's saying ionic concentrations are 1 mole per liter in water. Water is our solvent at 25 degrees Celsius. So they're being very specific about the concentration of the solution and the temperature at which the reaction happens that will result in particular cell potentials. Okay, so just to reiterate, the symbol for standard cell potential is this guy. Okay, and the unit, because it is measuring potential difference, is the volt. Okay, so let's carry on with this. So I want to talk to you a little bit more about the meaning of those values that we see in the chart, and then we're going to talk about how we utilize them. Okay, so we would say that the standard reduction potential measures a substance's likelihood of being reduced. So I'm just going to write out, and you'll remember that the oxidizing agent itself is reduced in a reaction. So let's say, for instance, I had, I'm going to use just Na plus randomly because it's a simple example. It's going to have to gain an electron in order to become solid sodium. And so when I associate a value for that standard cell potential, and let's look up that value. Okay, so I'm going to find sodium on here. And so when I look over here, I'm seeing that sodium has a standard, here it is, standard cell potential of negative 2.71 volts. So going back to my previous screen here, negative, 2.71, let's make that clear, volts. What this is saying, what this is describing is the likelihood of sodium to pull an electron towards itself and away from something else. Okay, so that is what this standard cell potential value is describing. And so it's describing its ability to pull an electron off of another substance. That's essentially what is driving that reaction in our galvanic cell, because you'll remember, and I'm just going to draw a really quick picture here to remind us, we've got these two half cell reactions joined by our salt bridge, right? And we've got our two electrodes, and we've got a voltmeter potentially measuring the current going through, right? And so if sodium is over here, sodium ions are over here, and there's another solution over here, you know, alternative, I don't know, some kind of solution, X plus, right? You know, these guys are in kind of like a battle for electrons. And so what this value is describing, this negative 2.71, is how strong sodium ions are at grabbing electrons compared to the other solution in the half cell, right? Because that's what's driving the reaction. If sodium is strong enough to grab those electrons, then it will, and that will create current. That is what is driving that electrical conductivity. Okay, let's move on. So now we're going to quantify things. So basically, let's go back here. I want to look at the chart. Basically, you should observe that when you start off at the top of your redox chart, the SOA, okay, our strongest oxidizing agent on this chart is our fluorine gas, right? And so with a standard cell potential of positive 2.87. And so what that's telling you is that it is very, very good at grabbing electrons. It would be a very strong oxidizing agent. In other words, it can be reduced very easily, right? And as we go down the list, as we make our way down this chart, you should be noticing that the values for standard cell potential, for reduction potential, are actually decreasing. And so it would make sense then, I'm hoping you're noticing that there's a certain point where the values become negative. And so when we quantify things, that is going to become important. Okay, so again, what are these values telling us? They're telling us the likelihood of a substance to be able to grab electrons from another species. They're kind of like in a tug of war. And the higher the reduction potential, the greater likelihood that it will be able to grab electrons and drive that cell potential, drive that cell potential. Okay, so as you would expect, the substance with the higher reduction potential is going to be reduced, and the other will be oxidized. Now, I want us to remember that the strongest oxidizing agent is the substance that is being reduced, right? And the substance that is being oxidized is going to be our reducing agent, right? And so the way that we calculate our standard cell potential, not just the reduction potential of a certain species, but this overall cell potential, okay, is we take the standard reduction potential of the substance that is being reduced, in other words, the SOA, that reaction at the cathode, minus, we're going to subtract that from the standard reduction potential of the substance being oxidized at the anode, in other words, our SRA. So I like to kind of sum it up that our standard cell potential is our SOA value minus our SRA value, just to simplify it. Let's take a look at an example. So in this first example, let me run it through with you. We have a galvanic cell and set up with a zinc electrode placed in a zinc nitrate solution and a copper electrode set up in a solution of copper 2 sulfate. Write out the relevant half reaction. So let's start there, and that's a good place to start regardless. You need to identify what your SOA and your SRA are, because that is the reaction that is happening in our galvanic cell. So unless we do that first, we're not going to be able to complete part B, which is to calculate the standard cell potential, right? So let's go ahead and do that. So take a minute, pause the video. I would like for you to go ahead and write out all your species, identify which are oxidizing agents and which are reducing agents, and then identify your SOA and your SRA in this scenario. So I've switched over to my redox chart and I've highlighted all the species that are involved. And I'm noticing that my Cu2 plus is highest, is the strongest oxidizing agent. So it's my SOA. And then I'm going to look on my I'm going to look on my reducing agent side, and I am noticing, and remember that on the reducing agent side, we're looking for the lowest species, and I'm seeing that that happens to be zinc. So zinc is my SRA. So, but I just want you to notice that I did highlight water because I have aqueous solutions. So just want to remember that water is a species that is kind of implied in that question, but not stated outwardly. So we need to remember that. But regardless, water doesn't seem to be involved in this reaction, and so I'm good to go. So I'm going to go back to the previous slide, and I'm going to write out the relevant half reactions. So I have my Cu2 plus 2 electrons going to give me copper. And then, and that is, that's a gaining of electrons, that's reduction, so that's my cathode. And then I have zinc becoming ionized at the anode. And so those are my two half cell reactions. Okay, and so when I look on my chart, I'm going to go back to do that. I can see what the standard cell potential values are here. So I can see positive 0.34. So I can write that out. And then I'm going to see the same value for my zinc. So for zinc, I'm seeing negative 0.76. Okay, so now I want to go ahead and calculate the standard cell potential in this case. And so you'll remember that the standard cell potential overall is going to be my SOA, the standard reduction potential of my strongest oxidizing agent, and a minus that of my strongest reducing agent. Okay, and so here I see the gaining of electrons, right? So it's being reduced. This is my oxidizing agent, and then the zinc is my reducing agent. So now I just simply have to substitute those values in. So I've got positive 0.34 volts minus negative 0.76 volts, giving me an overall value of 1.10 volts. And so just to mention, if we're looking at significant digits, remember when you're adding or subtracting, you want to conserve the number of decimal places of the value at the fewest. So I've got 2 decimal places and 2 decimal places. That's why I've written this as 1.10 volts. And I want to emphasize that this is positive 1.10 volts. And so I want you to keep in mind a couple of things, and I'm hoping that before I outright say it, this is a galvanic cell, and I have a positive standard cell potential. Let's take a look at another example. And so here's what I'd like you to do. I would like for you to try this example on your own, see how you do, and I would like for you to maybe make some conclusions about the value that you get and the sign of the value that you get. So pause the video, give that a try, and come back when you are ready. Okay, so I am switching over to my redox table here, and I'm going to start to highlight species. All right, so I have highlighted all the relevant species, and it looks to me as though Cl2 is my SOA. Remember, it's a solution, and so I need to consider the involvement of water. And so when I look at my species that are my reducing agents, it looks to me like water is my SRA. And so I have my relevant half cell reactions. So I'm going to go ahead and calculate. I've got the 1.36 volts and the positive 0.82 volts. And so I'm going to go ahead and calculate based on those values. So remembering that my standard cell potential is going to be the reduction potential of my SOA minus that of my SRA. And so I'm going to take my positive 1.36 volts and I'm going to subtract the positive 0.82 volts, giving me 0.54 volts. So hopefully you notice that that is a positive value. Now I want to just take a minute to take a look at the chart, and I'm wondering if you're making any connections here. So if I look at my chart, I'm just going to take a minute to circle the position of my SOA. It is here. And my SRA is already circled. I'm hoping you're noticing that right here I have a situation where my species are positioned so that this is a spontaneous reaction. So the lesson here is that the only way we're going to be able to drive this and produce electricity is if we have a positive standard cell potential. And if we have a negative cell potential, then that's indicating that the reaction is non-spontaneous, and we will need an energy source in order to kind of overcome that, that negative cell potential. So let's get a little bit of this down. So when we're predicting whether a reaction can be spontaneous or not, we can quantify it. We not only can just look at positioning, but we can actually do the math and see maybe what amount of energy is going to be required to drive to get this cell going. So we say that a negative cell potential indicates that the reaction will not occur spontaneously. There's a deficit there. Okay, the favored direction is the one where the standard cell potential is positive. Okay, so we've seen this before. Reactions can happen in both the forward and reverse direction, right? So for instance, let me just sort of give you an example. So let's say I have A plus plus an electron, and that's going to give me A. And I have a value here for my standard cell potential, and that's, let's say that that is like, I'm just making up a value, 0.50 volts, right? If I reverse that, then what I'm going to see is the opposite is true. So let's go ahead and try a question to help us practice this. So here is a typical example that you would have associated with the last little bit of note. It says, determine whether the following reaction is spontaneous in the forward or reverse direction. Okay, so we have copper reacting with hydrogen ions here, and copper ions reacting with hydrogen. And so they're not really telling us whether this is, water is involved here, whether this is aqueous or not. Although it's, without that, without the information, it's hard to tell. But let's take a look at our chart. So I'd like you to pause for a minute and locate all the species that may be involved, and then we'll just take a look at what we get when we calculate the standard cell potential. Okay, so in this scenario, I did include water just to be sure, because it doesn't hurt. But I noticed that my reactants here are Cu and H+. So I have highlighted them, and that allows me to see what my SOA and my SRA are. So in this case, it looks to me like the Cu is my SRA, and over here, my H+ is my SOA. Right? And so if I were to simply look at the positioning of these, it's clear to me that I've got my SRA above my SOA. And so I'm going to anticipate a negative cell potential here. But let's calculate that and make sure that we're correct. And so again, we know that our standard cell potential is going to be our strongest oxidizing agent's reduction potential minus that of our strongest reducing agent. And so substituting the values in here, we have our H+ as our SOA at 0.00 volts minus the positive 0.34 volts of our copper, giving us negative 0.34 volts. So that is telling me that in the forward direction, this is non-spontaneous. Okay, in the forward direction, I have a negative value, so that means it's non-spontaneous in the forward direction, which means that in the reverse direction, I would see that it is spontaneous. Okay, so let's just write that down. So since the standard cell potential is negative in the forward direction, the reverse reaction is spontaneous. And that is that. So let's try one last example. Okay, so determine whether the products or reactants would be favored. Then calculate the cell potential for the spontaneous reaction. Okay, I'd like you to give this a try. But before we do that, I just want to maybe discuss what it means for products or reactants to be favored. So if we're talking about a reaction that is proceeding in the forward direction, then we would say that the production of products is favored. If the reverse reaction is spontaneous, then that means that we're more likely to produce a reactant if that reaction is to happen kind of on its own. Okay, so just to explain the language there again, so if my products are favored, that's a forward direction. If my reactants are favored, that means the reverse direction is spontaneous. Give that a go, and then we'll check in together in a minute. Okay, so I've taken a few minutes to go ahead and simply highlight where my SOA and my SRA are. And I've taken note of their position in the chart just because I think that's just good practice. And I see that, I'm going to expect that this reaction is going to be spontaneous and that I should end up with a positive value for standard cell potential in the forward direction. But let's just do the math to make sure, and then we'll take a look at what we get. So again, I know that my standard cell potential is going to be that SOA value minus my SRA value for reduction potential. In this case, I'm getting 0.80 volts minus 0.34 volts, and so that is going to give me 0.46. And that means that this is a spontaneous reaction in the forward direction. So since it's spontaneous in the forward direction, I would say that products are favored. So hopefully you found that okay. All right, so take a look on Google Classroom for some practice questions for you to give a go, and reach out as always if you have any questions for me.